and I'm pleased to welcome you to this event as a scientific and technical manager of TraceBot, this EU-funded project in which we are looking at a very critical process of the pharmaceutical domain, that is the sterility testing. And we are looking at it from a robotic perspective, looking forwards its automation, and it raises many scientific and technical challenges that requires to gather cutting-edge technology in robotics. And I'm very pleased to be here today to share with my colleagues the recent developments and results we are having in TraceBot. And I think that with the program we have today, we will also enlarge the scope and look at different facets that has to be addressed to bring more robotics into the laboratory. So thank you for being here, and I wish you a very instructive day, and I hope with a lot of networking opportunities. Thank you for being here. Well, I will start describing this TraceBot project. So that is entitled Traceable Robotic Handling of Sterile Medical Products. So this is a running project. I will provide you a very short insight about the development that we are doing with all the colleagues involved in that project, and I guess that my colleagues later on during the session will provide more details about each of the different aspects. And what was interesting in that project is that yet from the beginning we have a clear view on the use case we wanted to focus, that is the membrane-based sterility testing process to verify whether a liquid is contaminated or not. And you see here the process being done manually by an operator. So it's clearly a critical process that is involved in the generation of many drugs and medicine. So its importance is very high. And we do believe that the different manipulation we observe there could be also, relevant for many other type of application. And what is also clear is that there are some evidences that robotic could make this activity. First of all, there is a concern about the risk of contamination of the human operator from the liquid manipulated, but also contamination of the human towards the liquid that has to be tested, right? The operations are quite long, repetitive, limited added value for the human doing it, and the environment is quite controlled, I would say. So many indications that robotic could have its place to perform this operation, but it's not yet the case. Why isn't it the case? There must be a lack of confidence in robotic solutions nowadays. Can we trust a robot performing such type of action? Can the robot do it nowadays? Do we have any evidence that a process done by the robot is indeed following the rules and verifying that the operation was done correctly? So that was the starting point of TraceBot a few years ago. Exactly 2 years ago. So TraceBot was born in that context. It's an EU-funded project, research and innovation, and it's composed of driven by the consortium that you see here. So Michael is coordinating from Bialago the activity of the project. On the left, Invite and Charlie Coulon and his team are helping us to define the use case and look at the regulation aspect. Aztec, that will present later our integrated system with Ben, is working on the integration of the platform we are developing. Bremen and Michael Beats will detail also their expertise that they are providing for reasoning about the operation of the robot. Theo Vien is involved with Marcus and his team on the perception aspect that is required. Sia is providing expertise in the design of dexterous gripper. And we as Tecnalia, we are working on the design of the control of the robotic system. The objective of the project was to promote the adoption, and is still actually, to promote the adoption of robotic system into the lab. In particular for any similar operations that are risky for the person and for the task itself, and that are repetitive. That's typically the operation we would like to be conducted by a robot, right? And it's a research and innovation action. So our objective is not to generate at the end of the project a product ready to be bought, but we see this use case as a good showcase of what could be achieved nowadays with cutting-edge robotic technologies in the laboratory domain. And we would like to bring inside a concept of agile production that are very trendy and used in more traditional industries, in which we are looking at robotic systems that are easy to program by non-specialists and also capable of adapt to slight changes of processes and product design. And of course, research and innovation action, we have to address also some very challenging technical points related to the different items that we have to manipulate. The objects are, as we will see, transparent, flexible. We would like to get a built-in verification and traceability of the operation conducted by the robot, and of course have a safe and failure-resistant system. These are aspects that are still, I would say, at the level of the state-of-the-art generation. But I have a limited time, and my colleagues will go into detail in many of the aspects that I will just very briefly mention, that are the 5 items that I listed here: perception, dexterity, robot control, tracing, verification, and reasoning. That are, few working directions that I just wanted to highlight today with you. So the first point, the perception. So if you want a robot to conduct the operation, the robot has to perceive the environment, has to detect the different objects to manipulate. And one of the challenges that we have here is that most of the items are transparent. And if we look at a typical scene, laboratory scene, and you try to look from the depth image that you can get the different item, the information is not complete. The transparency makes the life of the sensor quite complex. And even if you focus on the regular image, RGB image, well, what you see is what is behind the object. So the appearance totally depends on the background. So that makes the detection of such type of object quite challenging. Yeah. And so Vienne worked on an algorithm based on neural networks that is able to perform this challenging detection and pose estimation. So the technique is based on extracting some physics-based features that I will not detail now. I guess Marcus will come back to that point. Basically, they are looking at how the light is going through transparent objects to get some physics-related items that can be learned and then used by the neural network to detect this type of objects. And if you can see on that image, we are able to identify and to label different type of transparent objects that we are likely to manipulate in our desired environment. So message to take away that will be extended later on is that transparent object can be detected, localized with advanced vision technology. So we can perceive, but then we have to manipulate. How can we handle all these different items and use them as a human is effectively doing during the execution of the process? And that's where the CIA has been contributing significantly. And again, Mathieu will detail it in more extensively later on. But basically, looking at the different items manipulated and their 3D models, identifying during the manipulation which type of manipulation is performed, which fingers are involved in the manipulation. We can assemble these two information to get a merged map of relationship in between the objects and the hand of the human operator. And if you complete it with some information provided by the forces, interaction forces in between the human and the object, we can come up with all the information required to define the optimal grasping system that will be able to manipulate this object. And normally there is a video in the bottom right, if you can try to go onto it, but I'm pretty sure Mathieu will show more evidences of this system. And so CIA is working on the design of this modular 4-finger grippers that is currently being developed, and we are hoping to integrating it into our system by the end of this year. So we can perceive, we can manipulate, but we still have to handle the motion of the robotic system. How do we do that? So just a teaser, an example of manipulation that we're able to do today. All this is controlled by a skill framework. So when we talk about skill framework, we assume that the robot is equipped with a set of skills that are capabilities, motion capabilities, perception capabilities that are encapsulated into what we name here a skill. So that the process that we want to do is just, into brackets, a succession of skills that has to be executed, which is done by what we name a skill engine that will progressively execute each of the different operations. The interesting part of this framework is that as all the different behaviors are launched the same way, is that you can incorporate more constraint onto your system. You can incorporate systematic operation to be done at every time. And that's what we are using for the tracing. Aside the skill engine, we incorporate a tracer that will collect automatically, receive from the different skills, information about the starting condition of the skill, the exit condition, and also feedback during the execution of the process. And all this is collected automatically and then gathered to generate an audit trail that characterize the succession of operation and evolution of the activity conducted by the robot, so that we automatically get a trace of the activity that took place. Similarly, if we assume that these skills that are generated and implemented in the system are structured in a hierarchical way, so therefore based on intermediate sub-skills, I would say, then we can enforce the system to incorporate some verification processes. Verification operation, which purpose is, I would say, focus on verifying that the current task is done correctly, so that then we can automatically, again, collect that information and provide it into the audit trail to specify that the pose estimation has been verified and is correct according to our verification schemes. So the message to take away is here I will say that having a framework of control of the system, we can enhance the system with additional constraints and operation for tracing the operation, verifying the operation. Now, what we get here, I would say, is quite traditional because each of the verifications that we have to implement are, manually designed, manually implemented. So we will verify any step that we do implement, and therefore we are also looking at other ways of verifying and understanding the activity of the robot through the reasoning component that is developed by our colleague of Bremen. And so what we want to do here is to understand what's going on. So not from our perspective, but to give to the robotic system the capability to reason about its activity and therefore to be able to react if it is required. So here, two pillars that are developed. First one is what they name the digital twin, that is a simulated reproduction of the activity taking place. And just a small illustration here. So the video should start. Can I? No? Could you start the video on the right, please? And so during the execution of a task, all the information collected by the system, so the robotic position, the location of the object, are directly transmitted to the digital twin that will reproduce the action and reproduce as well the interaction in between the environment and the robotic system. So that the interesting part of this type of technology is that we can detect possible failures into the simulation before without having to implement a check into the real system, so that the simulation can provide us insights about deviation with respect to the plan. Another aspect of the reasoning system is the reasoning framework that we are using based on ontology, so that Bremen has been describing the whole environment with extending the ontology model with the description of the whole scene, the robot, the different objects to be manipulated, and they also incorporated a description of the different action. specifying what are the conditions to be able to launch an action. Like if we want to grasp an object, the gripper needs to be free of objects. And also describing the impact of an operation, like when we grasp an object after there is an object into the gripper, which means that we cannot do another grasp after all. So with all that information, the system is able to understand what are the current requirements to launch a new operation, and also to make sure that the expected conditions are reached to be able to launch a next operation, or even possibly, if we want, to reason and recover from failure detected and analyzed. So that we can use this system to inform about the appearance of object, like when we detect a canister into the environment, we can embed it into the world model that is progressively created, and then we can use this system to verify that from the data collected with the digital twin and the different sources of information, then the operation that we wanted to do, like inserting the canister into the tray, has been done correctly. So again, I guess that Michael will come back onto that point and provide more details about this technology that they are developing and inserting into TraceBot. I think my time is reaching more or less the limit, but that was the main points I wanted to highlight with you, and my colleagues will provide more details later on during the first session. So we are in the third year of the project. We have been having several progresses in different direction of the problematic. I mentioned dexterity, perception, the robot control, tracing, verification, reasoning. We are also looking at other aspects like the programming interface that I mentioned at the very beginning, how to demonstrate new behaviors so that the system can learn them, and also the integration is quite a big job, and Ben will present it later on, I think. We do believe that the different concepts we are gathering in this project could be applied to many other applications in the pharmaceutical domain, so we think it's worth doing all this activity. But of course, as I said, what we are developing is a demonstrator that illustrates the feasibility and the potential. There are still significant steps to handle before being able to deploy such type of system. One direction that is important to look at is how to find a good trade-off in between a human design process, like is nowadays the sterility testing that I illustrated at the very beginning, and a robot-friendly process. So we want to maintain a certain capacity of decision on the robotic side to take advantage of all the latest technology on the robotic aspect, but if the process is slightly robot-friendly, then the action will be more easily done by the robotic system. And if it's easier, it will be more robust, more reliable, and more likely to be accepted onto a real plant. Of course, depending on the concrete process we want to look at, there must be a proper selection of technology and hardware. We are here using a universal robot system because it's quite convenient for our early research perspective, but that type of robot is not likely to be the good size and characteristic to be provided into a grade A sterile environment, for instance. And of course, to go further on, we need to interact, to exchange with all of you to understand for some specific processes what are the specific requirements, and hopefully to progress in that interesting journey. And with that, I will thank you for your attention, and I'm pleased to answer to any question. Thank you very much.